So our lesson today is about mathematical induction. Mathematical induction is a way for proving some statements that concerns positive integers. This method of proving is very important, and it is often used in mathematics and computer science. It is very important actually, and we will learn this method today. So let me introduce what does it mean in general. If we assume that we have a Bn, B of n, which is a propositional function. Like Pn, we used to that might be, for instance, Pn, it might be the statement that says n is less than 2 to the power n. Or it might be some other statement like 3 divides n to power 3 minus n, where n here is any positive integer. So we will write it that way, positive integer. Okay, so the idea here, what we want is to prove that Pn is true, such a statement is true for all positive integers n. So how we do it? Using mathematical induction. The idea here is simple, but you need to pay attention to understand it. We will do it in using two steps. First, we call it basis step, in which we verify that the statement is true for n equals 1. So we started at n equals 1 and prove it is true for n equal 1. Just substitute n equals 1 in the statement Pn and see whether it is true or not. Okay, so once we do that, this is the basis step. This is the starting. So we had something to start. The proposition, the statement is true at 1. Okay, now what we do next? We go to the second step, which is called inductive step. And here it is important to understand. We show that the conditional statement, this conditional statement here, is true for all positive integers k. Okay, now this conditional statement assumes that pk is true, and then it uses this to prove that pk plus 1 is true. Now this is very important to understand. We are assuming the following. In here, we go down. Assume pk is true for an arbitrary integer k. Arbitrary integer. Okay? Under this assumption, we will show that pk plus 1 must also be true. Okay? Pay attention here. We are not assuming the statement p is true at arbitrary integer k. We are not saying it is true. What we are saying here, assume pk is true, then under that assumption we will prove pk plus 1 is true. So let me see it again. I will be repeating that again and again. So under the assumption that p of k is true, we get p of k plus 1 is true. Now this whole thing is called the inductive hypothesis. Here it is, the inductive hypothesis. It says that whenever p of k is true, then p of k plus 1 is true. If we can prove this, and we have the first step in here in hand, then mathematical induction will provide us a proof for the whole statement p of n. Okay? So the idea is the following. I would like to demonstrate it again. So in here we are saying that the statement p of 1 is true. Okay? Now in here we are saying that having the statement true at some integer k will give that the statement is also true at at the integer that comes after k, which is k plus 1. So assuming the statement is true at some integer gives that it is true also at the integer that comes after. So this thing, if we have it in hand, which is number 2 and number 1, if we have these two in hand, what we get? Now, P1 is true, then using 2, we get P2 is true. Okay? Now, P2 is true. Now, using 2 again, part 2, we will conclude that P3 is true. And now having P3 is true, then using part 2 again, we will have P4 to be true. And then P5 is true, P6 is true, and therefore P is true for any integer. So again, we will prove the statement is true at 1, and then we will show that under the assumption that the statement is true at k, then the statement will be true at k plus 1. Once we have these two things in hand, then the mathematical induction tells you the statement is true for any integer. Okay. Now, the mathematical induction is written, expressed in rules of inference this way. It says here, we have P if 1 is true, and we have this assumption. For every k, if pk is true, then pk plus 1 is true. So if we have these two things, this parentheses go with this, then we conclude Pn is true for every n. Okay? And the domain is the set of positive integer. So again, having the statement is true at 1, and having that under the assumption the statement is true at k, then it gives the statement is true at k plus 1. Having these two things in hand, then the statement is true for any integer. And for sure, to understand mathematical induction, we must work examples in details. And here we go. We start. And now, what I'm gonna do now here, okay, now what we write here is typical for what you will write when you prove by some statement by induction. First, we will use what is so-called, and I give them numbers, the paces step, which says that P1 is true. Now, is this statement P1 is true? What we are trying to prove here. What we will prove here is 1 plus 2 plus 3 plus 4 all the way till we reach some integer, stop at some integer n. That summation equals n multiplied by n plus 1 and then divided by 2. To understand the idea, let's try that. 1 plus 2 plus 3. Now this is n. Is it the same as 3 plus 1 over 2? And the answer is yes. Compute it. Now let's try it again. 1 plus 2 plus 3 plus 4 plus 5 plus 6. Now this is n. Let's see. N is 6 and plus 1 is 7 over 2. And this will be true. And also this will be true. So this is what we want to prove. 1 plus 2 all the way plus n equals n times n plus 1 over 2. So is the statement true for n equals 1? And just substitute 1 for n here, and then we got just 1 added 1 time. And that equals 1 plus 1 over 2. So this is n in here. So is that true? It is true, yes, because this is 1 at both sides. Okay, good. Now, the second step, which is inductive step. Okay, what inductive step says? The inductive step, now we will say assume P of K is true for an arbitrary integer. Arbitrary means any number. Arbitrary means any number. Okay. Arbitrary integer K. Now this assumption is what we call the induction hypothesis. Hypothesis. Okay, this is statement. Assume pk is true. What does that mean? Now, actually, if you go back, this is Pn. This is Pn. Okay? Now, pk is, so I'm explaining here what is the inductive hypothesis is. That is, we are assuming that 1 plus 2 all the way plus k equals k plus k, k times k plus 1 over 2. Okay? Now you may say, okay, how come you assume that thing? We are trying to prove it. How come you are assuming it is true? No, we are not assuming this is true for itself. We want to show that under this assumption, we said assume, right? Under this assumption, we will show that P of K plus 1 is true. So we will have this assumption in hand temporary, مؤقتا, to show that it is true for K plus 1. Once we do this, then we have the inductive step. Okay, now what do we want? Want to show that Pk gives P of K plus 1. So let me try here, right here. We want to show that if Pk is true, then Pk plus 1 is true. That's what we want, okay? Now we are assuming Pk is true. And then we want to prove this. Okay? So, again, let me write want Pk plus 1 is true, but that means now substitute in n here k plus 1 up there, so we will have 1 plus 2 plus keep going all the way k plus 1. So we keep going all the way till we reached here, and this goes for n. And this must be n, which is k plus 1, times n plus 1, which is k plus 2, over 2. This is what we want to show. And we have parentheses here. Okay? Now, if we can show this, using the assumption that Pk is true, then we are done. Okay. Now, let's write this part. Let us rewrite it. So we want to start in here and end up in here, right? So let's start. 1 plus 2 all the way plus k plus 1. Good? Equals what? This equals, now we know what this equals to. right? By induction. So I will write here, see what I do. I will make a long equality like this, equals, and I will write above in it induction hypothesis. This refers that I am using the assumption, which is BK is true. So I am using this, which we called induction hypothesis. By induction hypothesis, this equals K times K plus 1 over 2. And then this stays as is in here. This is waiting, okay? Now let us add them and see what we get. To add them, what we do, multiply, okay? Let me do that. Over 2 plus 2 times K plus 1 over 2. So what we got here, this is over 2, and now K plus 1 here is multiplied by K, and here is multiplied by K plus 2. So I can rewrite it K plus 1 times K plus 2. And here we go. We have reached this part. And then we are done. So good. Now, since P1 of 1 is true and P of K gives P of K plus 1, then P of N is true for every N belongs to the positive integers. How did we conclude that? You must mention by mathematical induction. And then we are done. Okay, so this is the first example. And then, okay. So this is another example to work with mathematical induction. Before we proceed to prove this example, let us try it and try to understand what this example is saying, what we want to prove. Just let's try it on some numbers so that we believe it. In here it says the assumption, that the summation. Okay, let me write it again. N, J from 0 to N, A to R power J. Now if you substitute 0 in J, then we get R to power 0, which is 1. Then we get A. And then substitute 1, we get that. Substitute 2, we get R square. And then we keep going all the way till we reach N. So this is N. This is the N that plays the rule. Now let's try that on some example. We want to show that this assumption equals A R to power N plus 1 minus A over R minus 1. Okay, so if we run it in an example to make some fun, so let's say G from 0 to 5, and we will say here 3 times 1/2 to power J. So we will get 3 plus 3 times 1/2 plus 3 times 1/2 square, and then we keep going all the way 1/2 to power 5. Now this is N. This is N. And this summation here equals A, which is 3, times R, which is 1/2, to power 6. This is N minus 1. Minus A, which is 3, over R minus 1, which is 1 minus 1/2. So now when we compute that, when we compute this side, it will be indeed the same as the summation here. And this is called geometric progression. And if you studied calculus 2, and you should, you have seen geometric series in calculus 2. But series goes to infinity, the n goes to infinity in here, n is finite. So we want to prove this using mathematical induction. So first, let us prove the basis step, which says this is B, basis step, which says that check this statement. Now this statement here, the whole this statement here, we will call P of n. Okay, because it depends on this n here. Okay, so P of 1, let's see what P of 1 says. So here it is n, so we have j equals 0 and j equals 1. That means a plus ar, and the question now, does it equal, if we substitute here a, now r, this is, it looks a to power r, it is not, it is a times r, a times r to power 1. Now here we will have 1 plus 1 minus a over r minus 1. Are they equal? Let's see that, if they are equal or not. So this gives a times r squared minus a over r minus 1. Take a to outside, we get r squared minus 1 over r minus 1. And then do the cancellation. This is r minus 1 and r plus 1 over r minus 1. Do the cancellation, and then we get a times r plus 1, which is ar plus a. So good, it is here, it is this one, so this is correct. So P1 is true. So we achieved the basis step. Now let's go to the inductive step. To the inductive step, which says at the beginning, assume ak, assume p of k is true for, so we will be repeating that statement, arbitrary integer k, and as before we call this the inductive hypothesis, and we will prove that assuming this is true, then p of k plus 1 is true. But let's write, what does that mean? P of k is true. That means if we add a to power r, a times r square, and then we keep going till we reach a times r to power k, and then p of k says this is the same as a times r to power k plus 1 minus a over r minus 1. So we have that assumption in hand. We are assuming that we have this in hand, and then we want to show that we can use it to prove pk plus 1 is true. So under this assumption, pk plus 1 is true. Under this assumption. Now, want to show that under this assumption, which means pk, we will get pk plus 1. So what is pk plus 1? So again, pk plus 1 says that if we add a times r square, all the way till we reach what? A times r to power k plus 1. And we want this to see if this equals, and it should equal, a r to power k plus 2. Because in here we ended with k plus 1, and this shall be k plus 2. Minus a over r minus 1. We want to prove that. If we can do it, then mathematical induction will prove the whole statement. Okay? And we will use the inductive hypothesis. Remember what the inductive hypothesis says. Okay, so we want to prove this quality. So we start with this side and then show it is equal to that thing. So let's start with it. A plus a times r square, keep going all the way, a times r to power k plus a times r to power k plus 1. Now, by the inductive hypothesis, we know what this thing equals. So again, we will write here inductive hypothesis. So when you prove using mathematical induction, you must do such a thing, and you must write the inductive hypothesis above there. So by the inductive hypothesis, this equals a to power k plus 1 minus a over r minus 1. Okay, and now we take this down here as it is, a to power r k plus 1. Okay, now we want to add them and see what will happen. To add these two things, we will simply just multiply this by r minus 1 from above and below, so that we change nothing. And then let's see what we get. We will have, once we do that, we will have r minus 1 here, and a to power r k plus 1 minus a plus, let's multiply, so we will do distribution. We will distribute this here over r and then minus over 1. So we will take, we will get this minus a to power times r to power k plus 1. And now you may notice that this part here will disappear with this part, and then we are left with I did not multiply correctly here, sorry. So when I multiply, I have a copy of r in here and in here, so I get this multiplication, the power will be k plus 2. So I will get a times r to power k plus 2 minus a over r minus 1. Great, and this is the same as that thing here. Now we must finish the proof by saying now we proved, this is now we proved p of 1 is true, and p k gives p k plus 1, and so by mathematical induction we have Pn is true for all n positive integers. And remember, Pn, what is Pn? The summation of the geometric progression. And I want to emphasize here what these things here means. It is true at p of 1, and now using this I can conclude it is true at p of 1 gives me it is true at p of 2. Using this again, now we have p of 2 is true, so using this again we will conclude p of 3 is true. Now we have p of 3 is true, and then using that we will get p of 4 is true, and so on. And this is another trial to illustrate how the mathematical induction is used. Use mathematical induction to prove that n is always less than 2 to power n, which is apparent. Okay, 5 less than 2 to power 5, 4 less than 2 to power 4, 2 less than 2 to power 2. Okay, but we need to prove it. We need to use mathematical induction. So one, we will start with, let me write here first, p of n means n is less than 2 to power n. Now the basis step, which is checking that this is true at 1, p of 1 says 1 is less than 2 to power 1, so this is true. So p of 1 is true. Second, the inductive step, it says that assume p of k is true for not for some, but for arbitrary integer, now arbitrary integer k, and we always meant that or we always mean that k is arbitrary positive integer. I did not write in the first two examples. So i.e. that is what we are assuming, that is we are assuming that k is less than 2 to power k. And now remember, all this is called the inductive hypothesis. So actually the inductive hypothesis is this part, okay? Now what we want to show that the assumption that pk is true will give that pk plus 1 is true. So let me confirm this, emphasizing this. Okay, but what does it mean for this to be true? That is, want pk plus 1 is k plus 1 less than 2 to power k plus 1. So this is what we need to prove. Okay, so let's go for it. So we start with k plus 1, and we want to show it is less than 2 to power k plus 1, and then okay, okay. So we want to start with, so some tricks are needed here. We want to start with k plus 1. So k plus 1, but I want to use this. So how may I rewrite things so that k is obtained in here? So actually k plus 1 is less than k plus k, correct? Because k can be any integer. It might be 1, so I will say less than or equal. Now each one of these, this one is less than 2 to power k. How did I know that? Using this. And again, I have another k here. And how did I know this? I will write here by the inductive hypothesis. Okay? And what this thing equals, it is 2 times k, 2 copies of it. So this is actually 2 times k plus 1. So okay, so we got what we want. K plus 1 is less than 2k plus 1, 2 to power k plus 1. And we will say now p of 1 is true, and pk gives pk plus 1. So by mathematical induction, Pn is true for all n positive integers. And what is Bn? Bn is n less than 2 to power n, and it is true for any positive integer. And then another example for mathematical induction, p of n here, it says 2n is less than n factorial, but not for every positive integer. It is for every integer n which is greater than or equal 4. So this is not true if n equals 1 or 2 or 3. Try to substitute that. 2 to power 1 is not less than 1 factorial. 2 to power 2 is not less than 2 factorial, which is 2. 2 to power 3 is 8, is not less than 3 factorial, which is 6. So Pn is wrong, it's false when n equals 1 or 2 or 3. But it is true when n starts from 4 and takes all integers after that. So the first step here, the basis step, will be p of 4 is true. So let's go for it. So 1, the basis step, which says that P of 4, it means 2 to power 4 is less than 4 factorial. Is that true? Computer, this is 16. True. Let's say true, because 16 is less than 4 factorial, which is 24, right? Now this is 4 factorial, and this is 2 to power 4. So P1 is P4, sorry, P4. P4 is true. This is the basis step. We did not start at 1. So mathematical induction, in mathematical induction, you can start, the basis step can be at 1 or 2 or 3 or 4 or any integer. You start with any integer, and then you prove the statement is true for all integers greater than or equal the one you started at. Okay, 2, we will go and do the inductive step, which says that now assume P of k is true for arbitrary, for any arbitrary positive integer k. That is, we are assuming here, assume 2 to power k is less than k factorial. And again, this is called the inductive hypothesis. Now, assuming this is true, can we prove that P of k plus 1 is true? If we can, then we got the mathematical induction proof for such a statement. So, okay, what do we want? Want to show that P of k gives P of k plus 1. But what is P of k plus 1? That means we want P of k plus 1 is 2 to power k plus 1 to be less than k plus 1 factorial. That is what we want to prove. Okay, using the inductive hypothesis. Okay, let us see. So usually we start with this slide in here, right? Now 2 to power k plus 1 is, and then we want to use this thing here. So we start with the left hand side of P of k plus 1, and we play with it so that some part of it comes out to be the left hand side of P of k. So that will be 2 times 2 plus k. So this is what I mean. This comes from P of k. And now this is less than 2 and k factorial. Okay, how do we know that? Because this thing is less than k factorial by what? By the inductive hypothesis. Okay, what do we want to reach? We want to reach this thing here, but we have k factorial times 2. How k plus 1 factorial is related to k factorial? Let me write it here. We know that k plus 1 factorial is k factorial times what? Times, so let me write them in order. It's k plus 1 times k factorial, right? So here we got it. So, but we have here k plus 1 times k factorial, and we have here 2. How 2 is related to k plus 1? 2 is less than k plus 1. 2 in here is less than k plus 1 in here. Why? Because k is assumed to be greater than or equal 4, remember? we assumed our domain is integers that are greater than or equal 4. And now we get k factorials in here. Oh, and this is k factorial, k plus 1 factorial. So we started with 2 to power k plus 1, and we showed that it is less than k plus 1 factorial. So we will write now p of 4 is true, and we showed that p of k gives p of k plus 1, and then we will write, so by mathematical induction, you have to write it completely. We proved p of n for n greater than or equal 4, and n is positive integer.